Hi guys, so in this video we'll be solving this problem minimum cost to connect the cities. Okay, so let's first understand the problem. So in this problem a graph will be given to us. The graph represents the connection between the cities, like the 0, 1, 2, 3, 4 are cities and these are connected by these roads. Okay, and this weight 10, 10, 8, 3, 3, this represents the weight, like the cost if we want to use this particular road, like 1 to 2. If but Here the problem is that initially these roads were there between these cities, like 0 and 1. They between 0 and 1 there was a road of land, means the cost was 10, but due to some earthquake or some disaster, these all these roads are now not like the earlier, like they are broken. So what is asked to us is that we want to rebuild this connecting this system, like we again want to connect these cities, but we want to do it in the minimum cost. What do I mean by it is that in if if I want to remake this road 0 to 1, then the cost will be what, 10. Okay, and if I want to remake this road the 0 to 3, then again the cost will be 10. So again this making this whole reconnecting means if we make all the roads again, then it will not be feasible. What we can do is that we can skip some roads. Okay, so it is asked to us what is the minimum cost in which we can connect all the cities. So this is what the problem is. Now let's see how we can solve this problem. The idea here will be is that, let's suppose if there is let's suppose three cities, 0, 1 and 2. Okay, and there is there are some roads from 0 to 1. There is a connection from 0 to 1. There is a connection. This is not directed connection, means by direction. We can go from 0 to 1 and we can come from 1 to 0 as well. And there is a connection from 0 to 2 and from 1 to 2. And let's suppose this the same case. Let's assume the same case over here also. Like initially these roads were present, but due to some disaster, now these roads are not there. Now we want to remake this system. So what the main idea will be is that why do we need to remake all the roads? What we can instead do is that there is a path from 0 to 1, 1 to 2. We can skip, we can erase, or we can erase this road also. Still we can reach. Okay, we can still reach all the cities. I can go from 0 to 1, 0 to 1 via 0 to 2 and 2 to 1. From 0 to 2 plus 2 to 1, I can still reach 0 to 1. So there is no need for multiple paths. Okay, if I want to minimize my cost, then there is no need to have the multiple cost. I will take the one which is the minimum. Let's suppose that the cost here is that this road is of cost 3 unit and this is of 1 unit and this is of 1 unit. So what I can do is that I can skip this particular road. Once it is broken, let's skip this road. Okay, or let's draw it over here. This means it is broken and we have not rebuilt it. Okay, and its cost was 3. Still I can reach all the cities. Yes, I can go from 0 to 2 and from 2 to 1, and the cost will be what, 1 plus 1, that is 2, and 2 is less than 3. Okay, so this is the idea what we are going to use over here also. We will not be remaking all the roads. Why to remake all the roads? Okay, since we want to minimize the cost. So this is the main idea. Now which roads to choose, like which roads to take, consider which one to remake and which one not to make, that is the point. So for that, what we'll be using, like this is a very common problem we have already solved the problem of this algorithm. Like if we want to connect some cities with the minimum cost, which algorithm we use like minimum spanning tree concept we use. Okay, so the same we are going to use. We will be using minimum spanning tree for solving this particular problem. So we will be using Prim's algorithm, and I hope you guys already know what is a Prim's algorithm. We have already discussed it earlier in our level 1 videos, but still let me give you a little bit of idea what we do in Prim's algorithm. The algorithm is almost exactly same as the BFS algorithm, but instead of queue, what do we use? We use priority queue. Okay, and we give the priority to the lowest weight. Let's suppose, what do I mean by it? Let's suppose if 2 is the source node, or not, let's suppose 6 as the source node over here. Okay, if I start from the 6th node, so there are two options for me. So I will have a priority queue. So what are the two options? I can make the road from 6 to 4, 6 to 4 via cost is 8. Okay, another option is that I can make a road from 6 to 5 via cost 3. Okay, and I will be using the minimum priority queue on the basis of weight. So which particular weight I will make the first, the one having the minimum weight, I will make that road first. So in my system, I will make a road of, let me do one thing, give me a second. Let me, yeah, this is visible. Okay, so what I will do, I will consider this particular road first. So I will make in the remaking process, what I will do, I will first make the road 625 via the cost 3. Okay, so now let's remove this one. Now I have reached to node 5. What are the options from 5? So I can make a road from 5 to 4 via the weight 3. So I will make this road first. So I will make another road in my system 5 to 4 via the cost 3. So this is, in this way, this whole Prim's algorithm works, and we will be able to remake the system in the minimum cost. Okay, still if you do not remember the Prim's algorithm, like, you can watch our videos. So now let's move on to the coding part. I guess the main idea of the algorithm is clear. Like, if there are multiple paths from same source to destination, we can skip some paths, since we want to do our work in the minimum cost. So we will only make those roads which are of the least cost, and we are still able to connect all the cities. And how to find those roads which are of the least cost and we can and still connect all the cities? So for that, we will use the concept of minimum spanning tree, and we will use Prim's algorithms for solving it. And what is the Prim's algorithm? I have told you, it is exactly same as, almost same as BFS. Instead of queue, we use a priority queue in it. Not BFS means Dijkstra, you can say it is same as Dijkstra. But Dijkstra means also depends on BFS. So yeah, directly we can say as BFS. Exactly same as means Dijkstra, but we can use priority queue over here. And in the priority queue, we give the priority to the minimum weight first. Okay, since because we want to make the roads in the minimum cost. Okay, so I guess the algorithm would have been clear to you till now. And now let's move on to the coding part, and let's see whether how it works. Okay, so now let's try to code this problem. So let's see how we'll solve it. So let's make a variable answer equals to 0. So as discussed, we will not be using all the means remaking all the roads. We will be using Prim's algorithm to find which roads we should make to connect all the cities in the minimum cost. So for Prim's algorithm, we will be using priority queue. Like, as I have told you, it is very much similar to the PFS or Dijkstra. Priority queue PQ equals to new priority queue. Okay. After that, in the priority queue, let's add new edge of 0 comma 0. Why I am doing this? Although it is like almost trivial, but let me tell you again why. We will start with, like, we will start from any source node, and it will give us the same answer. So what I am doing is that initially I am taking 0 as the source node and taking weight also as 0. Like, if there is only one city, then means there are no roads, so eventually cost will be 0 only in that particular case. So that is what I am doing over here. So initially I am pushing, means adding any, we can add any source node. So I am adding 0 with a weight of 0. So that is what I have done over here. So priority queue dot add edge of 0 comma 0. Let's, yeah, let me full screen it. Yeah, after that we had added the node. Yeah, so what will apply while priority queue dot size is greater than 0. What we will do, we will one by one remove the element. So removed element equals to priority queue dot remove. Okay, after that we will check, like, we check if it is already visited or not. So if this removed element dot v, if it is visited, then we will simply skip it. For that we will need to make a visited array. So let's make a boolean array visited equals to new boolean of vertices, where vertices are the total number of nodes in the graph. Okay, otherwise what we will do, we will mark it as what, mark this node as it is visited. Okay, we'll add it into the cost. We will add the cost in our answer variable. So answer plus is equal to what, removed element dot weight. Okay, after that what we will do, we will add it, means add its neighbors, all the neighbors that what we were doing over here. Like, if I was on the 6, when I was on the 6, what I was doing, I was adding the neighbor 8 and the neighbor 5 into the priority queue. So we will do that again over here also. So let's make array list of edge neighbors equals to graph dot get removed element dot vertex. Okay, now for edge edg in neighbors, edge edg in neighbors, what we will check, we will check if this neighbor is not visited already. Negation visited of edge dot vertex. So what we will do, we will add it into our queue. So we will add it into the queue, and finally when we are done with that, what we can do, we can print our answer. Okay, so I guess we are almost done with the code. Let's check whether we have written everything or not. We have made the priority queue, we have added into the priority queue, we have made a visited array, answer okay, adding the cost. Now let's try to run this code. Let's see if there is any mistake or find. Oh, there is a spelling mistake, it will be PQ. Are there any more mistake? Negation which add edge, negation widget edge dot q. Yeah, there is, I have written q instead of PQ at line number 51. It will be PQ, not Q. Since my priority queue, my name of the priority queue is what? PQ. Okay. I guess this was the error. Now let's try to run this. We are getting correct answer. Let's try to submit it. Let's see whether it is working fine. So it is getting accepted. So I hope you guys would have understood the video.